let's use the lowering operator to find the ground state wave function for the quantum harmonic oscillator. First, I'm going to write down the definition of the lowering operator in terms of the position and momentum operators. As we've seen in previous videos in the quantum mechanics playlist, A with a hat on top denotes the lowering operator. And we need a little coefficient out the front, which is square root of m omega over 2 h bar. And that multiplies this stuff in the brackets, which is the position operator, x with a hat on top, plus I over m omega times p hat. And p hat is the momentum operator. So a very important thing to notice over here is that we have a plus sign inside here. A dagger is the raising operator. So if we took the Hermitian conjugate, or the Hermitian adjoint of this operator, we would get A dagger. And A dagger is associated with raising energy states. Over here, we are lowering. So this is the lowering operator. What does the lowering operator do to an energy eigenstate? Well, if we act with A on an energy eigenstate labeled by lowercase n, that's going to give us square root of n times a new ket that has been reduced by 1. So we have n minus 1. We have lowered this state. So that is the action of A on an eigenstate labeled by n. And this is a normalization factor. That normalization factor ensures that we have the normalization condition satisfied when we act with this operator on this eigenstate. So this is the lowering operator expressed in terms of the position and momentum operators, and this is what it does to an energy eigenstate. And this relationship kind of looks like an eigenvalue equation, but it's not an eigenvalue equation. An eigenvalue equation would have the same eigenstate over here and over here. This is not the same eigenstate. You can see that this has the effect of lowering the eigenvalue over here. So the eigenvalue of the number operator gets lowered by 1. And the energy eigenvalue gets lowered by h bar omega. H bar omega is the quantum of energy for the quantum harmonic oscillator. So let's have a look at what we can do with all this stuff. First, I want to work in the position representation. So if I'm working in the position representation, then I want to write these operators in terms of the position representation. So what happens when I take x hat and I act on some arbitrary state? So this doesn't have to be an eigenstate. I'm just going to label it with psi. What happens if I take x hat and I act on this ket over here? In the position representation, this is the same as multiplying x by the wave function. And I'm going to write these brackets over here with x. That just says that this depends on the variable x. It depends on the spatial coordinate. And we're just dealing with one dimension over here. We will move on to the three-dimensional version of the quantum harmonic oscillator in later videos in the quantum mechanics playlist. So this is what the position operator does in here. So that's what we have here. We have the position operator. Now let's have a look at what the momentum operator does. The momentum operator, p hat, when it acts on some arbitrary ket, which is a representation in Dirac notation of a state vector, in the position representation, this is the same as h bar on I times the derivative of the wave function. So we are differentiating with respect to the spatial coordinate. And in general, we would need to write a partial derivative with respect to x. But because we're just dealing with one dimension and there's no time derivatives, there is no ambiguity if I just put the total derivative over here. So we're going to get an ordinary differential equation down below later in this video. So we don't have to worry about partial derivatives. But just know, in general, if you have other spatial coordinates or if you have time derivatives, this needs to be turned into a partial derivative. And you can equivalently write this with a minus I. So you can just move this I from the denominator to the numerator, but you have to introduce a minus sign. So this is the same as minus I h bar times the partial derivative of the wave function with respect to x. Now, what is something else that we need? We need to know what happens when we act on the ground state, because the whole goal of this video is to find the ground state wave function. So what happens when we take A, and we act on the ground state. So the ground state corresponds to n equals 0. Remember that n, this lowercase n over here, is one of the eigenvalues of the number operator. And those eigenvalues of the number operator are limited to the non-negative integers. So the smallest value this can take on is 0, and that corresponds to the ground state. So what happens if we act with the lowering operator on the ground state? Have a look at this normalization coefficient. We're going to have square root of 0. So this is just going to equal 0. This is one of the most important relationships that we're going to be using in this video. This tells us that when we lower the ground state, we get 0. So it disappears. The ground state disappears when we try lowering it. Physically, what does this mean? It means you cannot go any lower than the ground state. There is a lower bound to the energy. So this is what we're going to use, and we're going to substitute this definition into this expression. One more thing I want to define before I get started with the derivation is I want to define the ground state wave function. I'm going to call that psi sub 0, or psi naught. And this depends on x. It is a wave function that depends on the spatial coordinate. And we can actually write that in terms of Dirac notation. So this is the position representation of the ground state. So this is the same ket over here. We got the ket that corresponds to the ground state, and we're just taking the position representation of that. So this is a wave function. It's the same psi that we have over here, but we have a label, and that little subscript is a 0, and that corresponds to n equals 0. So that is all the notation that I need to do this derivation, to actually find what this function is. So what I'm going to do is I'm going to take this definition, and I'm going to act with all of these operators on this ground state wave function. And these operators are going to be written in the position representation, because I want the wave function in the position representation. You could also do this in the momentum representation, but it would be a little different. In the momentum representation, you would have a derivative appearing over here, and you would have multiplication by p appearing over here. So the things become a little bit swapped. And that comes from, actually it comes from the canonical commutation relation, which we talked about in a previous video. Position and momentum have a very special relationship in quantum mechanics. It's because they are non-commuting operators. So we won't go into that in this video. Now let's get started with this derivation. What I want to do is I want to take this combination and I want to act on this wave function. And that's going to give me 0. So I'll write that over here. So we're going to have this coefficient out the front, square root of m omega over 2 h bar. And in the brackets, this x hat is just going to turn into x because we're in the position representation. We're still going to have I over m omega. And what are we going to have for momentum? Well, momentum is going to be h bar over I times the derivative with respect to x. And I'll close this bracket over here. That ends this bracket. And we're going to be acting with this operator on this ground state wave function. That ground state wave function is psi sub 0, or psi naught. And I'll write the explicit dependence on x over here. And that's what these brackets denote. This is equal to 0. Now, I want you to notice that this relationship that I've written over here is equivalent to this relationship in the top corner. We are just taking the lowering operator and we're acting on the ground state. And that gives us 0. And that is just physically, what is that telling us? It's telling us that you cannot go any lower than the ground state. The ground state is as low as you can go. So let's have a look at what's happened inside over here. When we've substituted these expressions for the momentum and position operators, that's given us some interesting terms that are going to cancel. So position is pretty simple. It hasn't actually changed anything. We've just written x, so we're multiplying by x. And over here, some interesting things have happened. We have an I and an I in the numerator and the denominator. Those two factors are going to cancel. So we're going to get rid of the imaginary number I. And another thing that I want to mention is this over here, this combination in the brackets, this is acting on this wave function. So what this is actually telling us, it's telling us that x is multiplying psi, and then we're adding that to this derivative acting on psi. And when the derivative acts on the psi, that is the same as just taking the derivative of psi. Now, I'll write a simpler form of this expression over here. We can get rid of this coefficient out the front. This coefficient doesn't need to be there because this is equal to 0. and we can just divide both sides by this coefficient and get rid of it. And that's going to simplify the equation by a lot. So we'll get rid of this coefficient. Then in the brackets, we're just going to have x plus h bar over m omega. So that's what we got over here. We've got a h bar in the numerator, and in the denominator we have m omega. The i's cancel, and then we're going to have a derivative with respect to x, and all that is acting on psi naught. And from now on, I'm not going to write the explicit x dependence. So that is shown over here and over here, but we don't have to write the explicit x dependence. I think it's pretty clear from the definition above. And we know that this is equal to 0. So we have this combination of operators acting on the wave function that is equal to 0. And that's actually going to give us an ordinary differential equation which we can solve to find the wave function psi sub 0. So what is that going to look like? Well, I'll isolate it and I'll write it in a form that is very clear and more familiar. So we're going to take this derivative, we're going to act on psi naught. So I'll do that over here. We have the derivative of psi sub 0 or psi naught with respect to x. What is that equal to? So I'm just acting with the derivative. I'm going to have to divide both sides by h bar on m omega, and I also have to act with x on this psi naught, and I'll move that to the other side. So that's going to give me minus m omega over h bar times x times psi 0. So I want you to be very clear with how we got to this step. All I've done is I've expanded this out. So over here we have x times psi naught plus all of this acting on psi naught. And I've just moved that x times psi naught onto the other side. And that's where this minus sign has come from. And then all I've done is I've divided both sides of the equation by h bar m omega. And that's given me this m omega over h bar. That's just the reciprocal of that fraction. So that's how I've got this ordinary differential equation. Now, this might be familiar if you've looked at differential equations before. Another simpler version would be if we didn't have the x. If we didn't have the x over here, we would just have a function that is proportional to its derivative. Now, what function is proportional to its derivative? The exponential function satisfies that relationship. But over here, we don't have a function that's proportional to its derivative. We have a function that is proportional to its derivative, and over here we have another factor of x. So the derivative of the function is proportional to x times that function. So that is a slightly more complicated situation, but we can still solve this equation. So I'll do that over here. I'll solve this equation, but first I have to put it in a more convenient form. So what I'm going to do is I'm going to move all these x's to one side and all these psi zeros to the other side. So if I take all of the psi stuff to the left-hand side, that's going to give me d psi naught over psi naught. I'll just divide both sides by psi naught, and then I'll move this dx to this side over here by multiplying both sides of the equation by dx. That's going to give me minus m omega over h bar. So that's this coefficient out the front. And we're still going to have this x, and then we're going to have dx. So we have x dx. So what is that going to turn into? Well, we can integrate both sides of the equation now. This side only depends on x, and this side only depends on the ground state wave function psi sub 0. So if I draw a little integral sign over here, I can integrate this side, and I can also integrate this side. Over here, I could just factor this out the front, because this is just a constant. The mass, the angular frequency omega, and h bar are all constants. And we also have this minus sign, and this minus sign is very important. And this minus sign comes from moving this x times psi naught to the other side. So this minus sign is going to ensure that we have the function that we want to get. So now, let's actually perform the integration. If we perform the integration, what is going to happen on the left-hand side of the equation? Well, on the left-hand side of the equation, we have natural log of x, right? If you integrate 1 on x, you get natural log of x. But we won't have x over here, we have psi 0. So the variable that we're integrating with respect to is psi 0. And I'll write that over here, so we have some more room. So we're going to have natural log of psi sub 0 is equal to, what's going to happen on the right-hand side? Well, we're integrating x with respect to x. That's going to give x squared over 2. So we're going to have to divide by a factor of 2, and that's going to give us minus m omega on 2h bar times x squared, and we need to have a plus c, some constant, right? This is our constant of integration. This constant is necessary because we don't have any bounds over here. These guys are indefinite integrals, so we have to put a constant of integration over here. What can we do to this equation? Well, we can exponentiate both sides, and that's going to get rid of this natural logarithm. So if we get rid of that natural logarithm by exponentiating both sides, then what we're going to have is psi naught is going to be equal to e to the minus m omega on 2h bar x squared plus c. So I've just exponentiated both sides. Now, one thing I want to be very clear is we have a factor of 2 over here that has emerged. So this factor of 2 has actually come from the integration step. If you take this expression over here and you differentiate both sides of the equation, over here you're going to get back to 1 over psi naught if you take the derivative of natural log. And on the right-hand side, if you take the derivative over here, this constant is going to disappear. The derivative of the constant is 0. And this quadratic term is going to turn into the linear term that we have over here. But there's going to be a factor of 2 is going to come down when we take the derivative. And that factor of 2 is going to cancel with the 2 in the denominator. So that is why the 2 is necessary. The 2 has to be there so it can cancel out the 2 that comes down in the power rule. So that's just the power rule for differentiation. Now, this is what we have developed over here. That's when we exponentiate both sides of the equation. But have a look at this. We can use exponential laws, and we can write this in a slightly different form. We can turn this into e to the power of c times e to the minus m omega over 2h bar x squared. So all I've done is I've used some exponential laws, and I've split this up into the product of 2 exponentials. So if you split up those exponentials, then you can combine them back together, and they just turn into the sum inside the exponent. So that is one of those basic properties of exponentials. Have a look at this coefficient out the front. We have e to the power of some constant c. We can write that as just another constant. So we can write this as another constant. We can call that constant a. Right? We can call that capital A. That is the standard notation that is usually used for these normalization coefficients. So this is just some constant times e to the power of another constant times x squared. So I will tell you what that normalization constant is, and in the next video, we will actually find it. I'll do a derivation, and I will find the reasoning behind that coefficient. But I will write it down in this video. So in this video, what we found is that the ground state wave function, psi sub 0, and I'll write explicitly, this depends on the position coordinate x, that is equal to, I'll write the normalization coefficient. The normalization coefficient is m omega over pi h bar, all raised to the power of 1 on 4. And we'll see where that comes from in the next video. And then we have to multiply by this term over here, e to the power of minus m omega over 2h bar times x squared. And this function is called a Gaussian. We have a Gaussian function. And what does this Gaussian function look like? Well, it looks like this. I'll draw it over here. This is the shape of a Gaussian function. It looks like a bell curve. And you might have seen this in statistics if you've done statistics before. So over here we have a peak in the middle. And over here we have the x-axis. So this would be the x-axis. And this would be psi naught as a function of x. So it has a peak over here at x equals 0, and then it decays away. So most of the action is happening near the origin of the coordinate system. And you can imagine this as being embedded in some kind of potential well. And the potential well for the simple harmonic oscillator in quantum mechanics is a parabola. So you can imagine a parabola over here, and this is just sitting inside a parabola. We will talk more about the shapes of these wave functions in later videos. But what is very important to take away from this video is how we derived this Gaussian function. So all of these parts of the Gaussian function, they have come from this derivation. We started with the definition of the lowering operator. Then we knew that acting with the lowering operator on the ground state of the quantum harmonic oscillator gives us 0. That's because you cannot go any lower than the ground state. Then we used the position representation, where position is the same as multiplying by x, and momentum is this position derivative with h bar over I as a coefficient out the front. And we just applied that definition in the position representation to the wave function in the position representation of the ground state. And that gave us this ordinary differential equation, which we solved by using this little technique over here. We just moved all of the psi naughts onto the left-hand side, and on the right-hand side, we just had everything involved with x. And this integration is where the x squared came from. That's why we have an x squared up here. This minus sign came from moving this to the right-hand side. And this exponential part came from exponentiating both sides because we had a natural logarithm that emerged from doing this integral. In the next video, I'm going to derive this guy over here. And that's going to come from taking the integral of the Gaussian. So the integral of the Gaussian is actually a little bit complicated. So it's not one of your standard functions. It's not usually taught in high school calculus, right? Because this has a few extra steps. We're going to have to go into polar coordinates. There are other ways of doing it, but in the next video, I'm going to use polar coordinates to take the integral of this, actually the integral of the square of it, and that's going to give me the normalization coefficient, which is given by this. So this notation over here, psi sub 0, that is just standard notation for the ground state wave function. In later videos, we'll also find some excited state wave functions. So those are those higher energy states that have more energy, and they're going to have more lumps and bumps. So it's not going to be just a simple Gaussian, it's going to be a Gaussian times a polynomial. And that's going to give us some more interesting shapes. And make sure to find those videos in the quantum mechanics playlist. You can find them if you click over here.